Welcome to the 81st Theoretical-Physics-Colloquium by Professor Simon Hentz, who's a professor of theoretical physics at the University of Liverpool and community development director of the Iraq High Performance Computing at Liverpool. He got his PhD in 1986 from Edinburgh University, had several postdoctoral positions at Oxford, University of Illinois Urbana-Champaign, University of Glasgow. Then he received a Science Engineering Research Counseling Fellowship at the University of Glasgow and a CERN Fellow in '92 at CERN. He moved to Swansea in 1993, where he was a faculty until this year, actually, and he moved to Liverpool in 2021 in August. He is an elected fellow of the Learned Society of Wales, which the distinction which he received in 2013. In 2015, he became a Royal Society Leverhulme Trust Senior Research Fellow, and in 2021, Outstanding Reviewer for Physically Reviewed Journals. He served also in the professional capacity as on the editorial board of European Journal of Physics A for 7 years between 2010 and 17. His research interests include lattice QCD, thermodynamics and transport properties of QGP, Monte Carlo simulations of low-dimensional systems, including graphene, dense, two-color matter, Thirring Model, and many other things. And today he will be talking about advances in flatland, quantum criticality in the 2+1d Thirring Model. And with that, I'll give the microphone to Simon.
Thank you, Igor. Thank you for that introduction. And thank you for inviting me to talk today in this fantastic seminar series. So can everybody see the slides and the cursor?
Yes.
Thank you. Thank you. Okay, let's get underway. This is essentially a talk about quantum field theory. And quantum field theories in particle physics, for the most part, are weakly interacting at short distances. And what that means is, that's good news. It means we have a reasonable idea of how to calculate with them. We can apply perturbation theory through the fantastic technology of Feynman diagrams. We're also able to apply non-perturbative techniques such as lattice QCD, which are well defined and under control because QCD is weakly interacting at short distances. But that really doesn't exhaust the only possibility, the only quantum field theories we can think about. And I'm going to discuss today what happens if the field theory is strongly interacting at short distance. I'm going to draw inspiration from condensed matter physics, and in particular the condensed matter physics of layered systems, two-dimensional systems, and the kind of famous one is graphene. So I'm going to discuss those field theories and in particular highlight the possibility that they have some kind of critical behavior. In other words, there's some phase transition going on, and at that critical point there could be a new, strongly interacting quantum field theory, hitherto unexplored. I'm going to argue, certainly very non-rigorously, that in order to accurately characterize that critical behavior, it's crucial to capture the relevant global symmetries accurately, faithfully, and that's not a gimme. And that, in fact, it's going to turn out that different ways of discretizing the theory on a space-time lattice can actually give you different stories, different results, and that's interesting in itself. So that's more or less the outline of the territory we're going to cover. I'm going to focus almost exclusively today on a particular field theory, the Thirring Model. So in the top left there is a photograph of Walter Thirring, and I'm slightly abusing his legacy here because I'm choosing to define the theory not in 1+1 dimensions, where he started, but in 2+1 dimensions. It's a covariant quantum field theory of interacting fermions. The things I need to tell you are that the The fermions are described by spinor fields with 4 components. They're what's called a reducible representation of the rotation group in 2+1 dimensions. So you can see there's a standard kind of kinetic term here for the free non-interacting fermions, and then there's an interaction. It's a contact interaction between 2 fermion currents. Those currents are conserved. That means there's a conserved charge. So the Thirring model, on the face of it, has many features in common with Abelian gauge theory, with QED in 2+1 dimensions, which is also a theory of interacting currents. And in particular, the heuristic that because I can assign a charge to my excitations, we have the rule that like charges repel and opposite charges attract. So if you've not come across the Thirring model before, that's the essence of it. Of course, exactly how that repulsion and attraction works depends on the details of the dynamics, and we'll be looking into that. So here are some definitions of the Dirac algebra, which are needed, stressing again that I'm using 4-component Dirac fermions, and I'm going to be in Euclidean metric throughout. So gamma 5 is defined there without a factor of I. So why should we be interested in fermions moving around and interacting in 2+1 dimensions? Most of the physical applications of flatland fermions come from condensed matter physics. I'm listing just a few impressive sounding topics here. If you go to D-wave superconductors, so we're in these are cuprate superconductors. If the superconducting condensate forms in a D-wave, it means that there are 2 pairs of nodes at the Fermi surface around which excitations are approximately linear in energy as you move away in momentum space. So therefore, you can define a theory of fermions with linear dispersion there, and that could be a relativistic fermion. Another example is in the spin-liquid phase of Heisenberg antiferromagnets, where spin and charge degrees of freedom become separate. And again, there's a region there where the best description is in terms of interacting Dirac fermions. A topic we heard about last week from Professor Sen. There are insulators, so that in other words, the excitations are massive or gapped within a bulk, but they have edge states which can be massless or relativistic. So theories of surface states of topological insulators can also be relativistic fermions. I'm going to focus in the talk, for heuristic reasons, on kind of, I guess, the most famous example, and that is electronic excitations in graphene. So as I'm sure most of you know, graphene is electrons moving about on a 2-dimensional honeycomb lattice, a single atomic layer of carbon atoms. So here's my honeycomb lattice here, and the really important thing about the 2 features of this lattice which are important for graphene is, first of all, it's bipartite. There are 2 different kinds of site. There are A sites and there are B sites, and so the actual physical lattice of the repeating unit cell of the real lattice actually has an A site and a B site. And also all the bond angles here are at 120 degrees rather than 90 degrees. And this is going to turn out to be important. So for neutral graphene, there's 1 loosely bound or mobile electron per lattice site, which can hop between sites. If I hop along 1 sort of elementary lattice distance, I'm always going from a B site to an A site or an A site to a B site. So therefore, this very simple tight binding Hamiltonian is the basic object which describes this kind of electronic motion. It's most convenient to look at it in momentum space. So I've just Fourier transformed. I've got operators here which create and annihilate electron degrees of freedom both on the A sites and on the B sites. And these kernel functions, capital phi here, are complex valued. In fact, I've written down here, you can see there are factors of I, as well as interesting factors of √3. The fact that they're complex is a consequence of the fact that there are no right angles in a honeycomb lattice. So that for every bond, there's not an equal and opposite bond in the opposite direction, which would give a complex conjugate factor. So we can go ahead and diagonalize that Hamiltonian with a suitably chosen basis of states. The spectrum, the energy as a function of momentum, is symmetric about 0. And in fact, there are 6 points in the Brillouin zone where the energy vanishes, and it vanishes in this particularly interesting way. It's like 2 touching cones, where the cones just touch at the apex. And so in the neighborhood of those Dirac points, the dispersion is linear. Energy is a linear function of momentum. So within that Brillouin zone, there are 2 independent points. They're called Dirac points, where I can choose to focus my analysis. And if you Taylor expand this kernel function phi around those Dirac points, 2 things emerge. First of all, it's linear. The constant of proportionality relating the energy to the momentum is the Fermi velocity. But also that there's a relative phase of pi by 2 between the y component and the x component. And again, that's a consequence of starting with a honeycomb lattice. That's where that's where those factors of I came from. The pitch of the cone, the Fermi velocity, can be related to the fundamental lattice parameters and tunneling strengths in the original Hamiltonian. And what it means is that if you go away and look up what those numbers are, then the Fermi velocity is not the same as the speed of light. It's about 1/300th of the speed of light. However, it's now possible with a little bit of very simple algebra to rearrange the fermion operators, arrange them into groups of 4, 2 of them based on A sites, 2 of them based on B sites, and each of them based around one of the Dirac points. And if you rearrange it, then the Hamiltonian can be written in this form with a 4×4 matrix, and the 4×4 matrix is basically the same as the Dirac Hamiltonian for relativistic electrons moving in 2 spatial dimensions. These matrices alpha here obey anti-commutation relations of this form. So it's really the case that the low energy excitations in graphene are relativistic. As I said, it's not the physical speed of light, it's 1/300th of the speed of light. That's still pretty fast. For monolayer graphene, if you have a single sheet of carbon, there are 8 degrees of freedom per unit cell in all. So it's natural to, when you recast it as a relativistic theory, to think of it as 2 flavors of 4 component spinor. That's a convenient way of thinking about it. So already we're coming up with the idea that there is a number of flavors associated with this model. And for this particular case, it's n = 2. I'm very happy to pause and ask for questions. I'm sure most of the audience know this material pretty well by now.
So far, there were no raised hands, though.
Okay, that's good. I'll press on. Okay. Well, to go further, we need to think about introducing interactions between the electrons.
Sorry, Simon.
Go ahead.
As I said it, there is a raised hand. Rob? Go ahead.
So if I take different symmetries on a different kind of lattice, can I get different numbers of flavors?
I guess you can, yeah. I mean, we know that if you work on a cubic lattice, you end up with staggered fermions, and actually, coincidentally, in 2 spatial dimensions, staggered fermions gives you two component spinors. If you discretize the 3rd dimension, you get 2 4-component spinors. So that's an obvious answer off the bat, and I'm sure there must be lots of.
I was thinking of more. If you had something with 8 points, or something.
I don't know. You know, there's been a lot of work. I mean, actually started off by Mike Kreutz, thinking about hyperdiamond lattices in higher numbers of dimensions. So generalizations of a honeycomb. And the idea, the hope there, that driving that program was to come up with an action with a smaller number of flavors, a minimal number of flavors, consistent with Nielsenninomia. I don't have anything.
No, I asked because the question of, as the number of flavors gets big, do you lose chiral symmetry breaking?
Okay.
Flavor symmetry breaking. Okay, thanks.
I haven't think about that, but you know, symmetry is embedded in this talk, so maybe let's press on and see where we get. Okay. It's appropriate to think about the because the density of states at the Dirac point vanishes. Coulomb interactions between the electron-like excitations are unscreened. So it's appropriate to model interactions in graphene as some kind of electrostatic interaction. And that's what this Lagrangian here does. I'm not going to go through it in detail because I'm not going to work with it today. But essentially, here are the fermions, degrees of freedom, moving around in 2 spatial dimensions, interacting with a dynamical electrostatic potential here, but the electrostatic potential is governed by a 3-dimensional action, or 3 + 1 dimensional action, sorry, because so in some sense this is an example of a brane world. The fermions live on a 2-dimensional brane, but they interact with photons moving in a 3-dimensional bulk. If I think about, just look at what this theory looks like. Of course, I've got the classical Maxwell term. I can describe that simply by an undressed photon, and that that's going to decay as 1/r, because that's what the Coulomb potential does in 3 dimensions. But I can also think about the dominant quantum correction, which is due to a particle-hole pair, a virtual pair. This diagram is pretty easy to evaluate once Rob Pizarski has told you how to do it. And the answer is that in 2 + 1 dimensions, it also goes as 1/r. So that leads to an interesting kind of standoff, because we've got a classical term and a quantum term. They're both giving roughly the same behavior. And I can kind of parameterize the extent to which classical physics is important, or the extent to which quantum physics is important, by this dynamical, this dimensionless ratio lambda here, which depends on the number of flavors, and interestingly also depends on the relative electrostatic permittivity of the which pertains to the graphene sheet. This is relevant because the very first samples of graphene were all made on a silicate substrate. So this relative permittivity epsilon was a number greater than 1. And kind of the hope was that if you could actually have a free sheet of graphene, what's called suspended graphene, then epsilon would be 1. That would actually lead to stronger interactions. And maybe that would lead to something interesting. Okay. Well, here's what it may lead to. This is a fairly general argument. If the coupling constant G, I've suddenly started calling it G squared rather than E squared, but if the coupling strength gets large enough, and if the number of flavors, the number of Fermi degrees of freedom is small enough, it's plausible that the non-interacting ground state we've been talking about, the Fock vacuum, could be disrupted by a particle-hole condensate. And we can, in other words, I can think about there being some kind of scalar function made up of a fermion and an anti-fermion, coupled with a mass term, with a mass parameter m. Then the derivative of the free energy with respect to m would lead to something non-zero, and that would result in a dynamically generated gap at the forming at the Dirac point. This would turn graphene from a conductor into an insulator. Now, of course, for QCD people in the audience, many of us come from this side. This is a very, very familiar story. This is exactly analogous to chiral symmetry breaking in QCD. There is some particle-antiparticle condensate forms, which leads to dynamical mass generation. I think the idea came up several people simultaneously, but I was drawn into this game by reading a lovely paper by Damson, who postulated that there indeed a critical value of the coupling would exist above which this condensate would form, the gap would form. And in fact, exactly at that critical value, there would be a quantum critical point, possibly leading to modifying the long-range properties of the electronic excitations of graphene. If that critical point were to exist, it would be described by a strongly interacting quantum field theory. And because G is large and N is small, there are no small dimensionless parameters in the game. Therefore, it's an intrinsically not just a non-perturbative problem, but a difficult non-perturbative problem, one in which, in fact, our best hope may, to find a solution, may be involving numerical simulations. Again, this is a good point to pause and ask for questions.
Okay, go ahead, Rob.
I just wanted to say, although they didn't phrase it in these terms, the idea that in 2+1 dimensions, there's a critical NF, which is not the same as your G squared, was due to Appelquist and Via-Vardhana and others, based upon the Nambu-Gianlucinio analysis, that there has to be some critical coupling. So
Sure.
I just wanted to make that as a
Yeah, thanks. Yeah, in fact, I'm going to argue that there's a critical number of flavors in this in the Thirring model, which is the one I'm going to play with on the next slide. In fact, yeah, I agree. Yeah, I'm coming at it from the graphene perspective because it's a neat way into the problem. It's not a historical way into the problem. Okay. Just to reiterate why the link between quantum field theory and criticality. This is kind of almost undergraduate material, but I'm gonna go through it anyway. Here are three different views of a substance called sodium hexafluoride, taken at 3 different temperatures. One below a critical temperature where there is a clear separation into a liquid phase and a vapor phase. And you can see the separation between them. It's called a meniscus. If you go above the critical temperature, and you can see this, it's the same cell, but now at a higher temperature, there isn't the distinction between the vapor and the liquid has gone. If you tune the temperature of the cell to exactly the right critical temperature, then something remarkable happens. It goes misty. You can't see through it. This is a phenomenon called critical opalescence. What's going on is that at this point, the system doesn't really know if it consists of large droplets of liquid inside a vapor, or maybe large droplets of vapor inside a liquid. There are inhomogeneities, and the characteristic scale of those inhomogeneities is large. In particular, it's large compared to the typical separation between. So here's the size of the droplet. It's given a. I'm going to denote it by a symbol xi. In general, this stands for something called the correlation length, the typical non-trivial correlations between interacting degrees of freedom. And I'm going to compare that with the typical separation between molecules, so I'm going to call A. So in a critical state, this ratio of xi to A, the ratio of kind of correlated degrees of freedom compared to their average separation, is large. And in quantum field theory, we have the same hierarchy. We talk about an ultraviolet scale, where we have to regularize our theory, and we talk about a physical scale, which characterizes the physics we're interested in capturing with the field theory. That could be related to a scattering cross-section, or it could be related to a particle mass. In both cases, the interesting regime is when this ratio becomes large. That large values of that ratio characterize what's called a critical theory, and it's where quantum field theory is interesting. Okay. The next thing I want to cover is the symmetries. I'm going to argue a big theme of this talk is going to be that in order to capture critical behavior properly, you need to get the symmetries right. So what are the symmetries of relativistic fermions in 2+1 dimensions? Remember that these are fermions with 4 components, so the gamma matrices have 4 by 4 objects. The kinetic term has gamma matrices gamma 0, gamma 1, and gamma 2. And that means that there are 2 other gamma matrices which anti-commute with the kinetic term. That's gamma 5 and also gamma 3. And what that means is there's actually quite a rich set of rotations I can perform on the fields, leaving the kinetic term invariant. There are 4 different kinds of rotation. I can either just do a straight rotation, or I can rotate with a gamma 3, gamma 5, or just with a gamma 5, or just with a gamma 3. If I introduce a mass term, which is the gapping which occurs when the condensate forms, then these 2 rotations, the gamma 5 and the gamma 3, are no longer symmetries. And so gapping or mass generation results in a symmetry breaking. Because there are 4 different rotations, that generates in general a U2n. When the spontaneous symmetry breaking occurs through generation of a term like this, that breaks the symmetry to un cross un. That mass term is Hermitian in Euclidean metric, and also it has the important property that it's invariant under parity, invariant under inversion of all 3 space-time axes. There are 2 other physically equivalent mass terms I can write down, which share the parity invariant property. And there's a mass term with a gamma 3 sandwich between and a mass term with a gamma 5 sandwich between. So from the perspective of continuum field theory, these 2 mass terms are physically indistinguishable from this one. In the world of graphene, they are distinguishable, and they're called Kekule mass terms. They correspond to a charge density wave which forms on alternate bonds. There's actually a 4th mass term I can write down in 2+1 dimensions with a gamma 3 and a gamma 5. And this one is not parity invariant, as pointed out originally by Rob, as he told me last week. But it also did wonders for Duncan Haldane because it corresponds to spontaneous time reversal, explicit time reversal invariance, which means you can get some interesting effects in particular models. But because it's not parity invariant, I'm not going to talk about it any further in today's talk. Okay. I hinted already that the non-perturbative technique I'm interested in applying, or I know how to apply to these systems, is lattice simulation. So I've actually been on this game quite a while. In the earliest simulations I did, I used a cubic lattice. Remember, I'm doing 3 space-time dimensions. And here is the Lagrangian I used. It used a formulation of fermions called staggered lattice fermions. And the 4-fermion interaction is actually encoded by introducing what's called an auxiliary field, which lives on the links of the lattice. So the fermions live at the sites. The auxiliary field lives on the links. When you integrate out the auxiliary field, because it's only there with a Gaussian weight, you actually recover a 4-fermion interaction between a psi and a psi bar here and a psi and a psi bar on the adjacent site. If you look at it closely, it's a little bit like a gauge theory. It shares some features, and the A field in particular looks a little bit like a photon field. It's not a photon field because this term is not gauge invariant. And the other important difference is that the way it couples to the fermions isn't through a unitary e to the ia, it's actually through a non-unitary 1 plus or 1 minus ia on the links. That's going to turn out to be numerically quite an important distinction. Another important distinction, which I didn't worry about at the time when I started this game, was that the symmetries of staggered fermions are not the same as the symmetries of continuum fermions. They actually have a un cross un symmetry, And when the gap forms through a term like this, that breaks spontaneously to UN. Now, when people use staggered fermions in QCD, they don't worry that the symmetries of staggered fermions are not the same as continuum fermions, because it's believed on very strong, firm grounds that in a weak coupled continuum limit, the continuum symmetries are recovered. And indeed, if that were the case in 2+1 dimensions, that would mean that actually if we went to weak coupling, we would eventually recover a U2NF symmetry, where NF, the number of continuum flavors, is actually twice the number of staggered flavors. That factor of 2 is a consequence of something called lattice fermion doubling. And the phenomenon I'm talking about in the world of QCD, it's known as taste symmetry restoration. It means that it's viable to use staggered fermions to talk about QCD. However, the physics that I'm interested in at this putative quantum critical point, that's strongly interacting. And there is no reason in general to suppose that taste symmetry restoration happens at a strongly coupled fixed point. So I should have worked this out a long time ago. It's taken me a long time to learn this lesson. But I pressed ahead, and over a series of papers, we worked out this phase diagram for the Thirring model defined with staggered fermions. Across the horizontal axis it's actually inverse coupling. So coupling is getting weaker as I go to the right. It's stronger as I go to the left. The vertical axis here is the number of flavors. And what we were able to show is that if the number of flavors is large or the coupling is weak, in other words, to the top right of the diagram, then no condensate forms. We're talking about an ungapped or conducting phase. And if I've got a small number of flavors and the coupling is strong, then the condensate forms, and I've got a gapped insulating phase. What's interesting about plotting the results in this way is that it focuses attention on the strong coupling limit for various technical reasons I don't want to go into unless someone's interested. The strong coupling limit actually exists at a non-zero value of 1/g². But the number of flavors corresponding to the strong coupling limit is called the critical number of flavors in the model. So the critical number of flavors is an important number to know when one's talking about this particular system. And it's, in general, a tough problem in non-perturbative field theory to work it out. So these lattice simulations have come up with a critical number of flavors, an estimate, which is just a little bit above 3. Okay, why is it important to get the symmetry right? I'm going to give you a plausibility argument based on 2 old conjectures, neither of which are proven rigorously, but so this is kind of hand-waving and provocative. It's not supposed to be the last word. It's possible to study the Thirring model in the 1/n expansion, in the large n expansion, and in the strong coupling limit, you can actually come up with an estimate for the mass of the vector boson, which mediates the interactions between the conserved currents. And the mass of that vector boson actually vanishes in the strong coupling limit. If you have a theory of conserved currents interacting via massless vector boson, that sounds a lot like QED in 3 dimensions. So it's at least plausible that the strong coupling limit of the Thirring model, in other words, the model defined with the critical number of flavors, is equivalent to the infrared limit of QED3, which is a theory which has also been postulated to have a critical point, but this time in the infrared limit. What can we say about QED3? Well, there's a very interesting paper written by Appelquist and collaborators around about the turn of the century, who postulated that any asymptotically free theory must be constrained by some inequality, roughly to do with counting the number of degrees of freedom of the effective descriptions either in the infrared limit or the ultraviolet limit. I don't want to go too much into this, but it coincides with the thermodynamic free energy density, this function f. Rather than try to justify that to you, I'm just going to tell you what answers they got. If you apply their arguments with staggered fermions, here's the pattern of symmetry breaking for staggered fermions. Well, in the infrared limit, if symmetry is broken, we know that the number of infrared degrees of freedom is the number of Goldstone bosons, that's n squared. We can count the number of degrees of freedom in the ultraviolet limit. It's the number of poles of the fermion propagator times the number of flavors times a magic factor of 3/4, which accounts for the Fermi-Dirac statistics in 3 space-time dimensions. That gives you this inequality. In order for this inequality to be satisfied, that tells you that the critical number of flavors can be no bigger than 6. And that's fine because we found a critical number of flavors of 3 in our simulation, so we're apparently consistent. But if I apply the same arguments now to the continuum theory with symmetry breaking U2n goes to un cross un, then I get twice as many Goldstone bosons on the left-hand side and half as many fermion degrees of freedom on the right-hand side. So that gives me a much more stringent constraint on the critical number of flavors for continuum fermions. The critical number must be less than 3/2. And that was the prediction that Appelquist and company made for QED3. And that big disparity is a worry. It tells you that symmetry matters. I should add that it's possible to do a more sophisticated and possibly more rigorous job of constraining the critical number of flavors using something called an F theorem. And this takes into account that the actual effective description of the theory at the critical point is not a free theory, but rather an interacting conformal theory. You have to work harder, and these authors did in 2016, and they predict a slightly less stringent bound of 4.4 for the critical number of flavors.
Simon?
Yeah?
Quick question regarding the staggered fermion formulation. When you're considering the symmetry, you're talking about the symmetry for the fermions.
Yes.
What's the gauge symmetry in the two models? Is it both cases UN?
There isn't. It's not a gauge theory. Is the answer?
But you have gauge bosons, so it's
well,
not
I
a gauge symmetry.
I have something which looks like a gauge boson, but if I go back to the action, sorry. The action for the A field is just a simple Gaussian weight, and that's not gauge invariant.
I see.
That's because A is an auxiliary field. It's like the Hubbard-Stratonovich boson.
But what confused me then is the statement that essentially QED3 is like the second formulation. So in the QED3, we do know that there is gauge symmetry.
Yeah. So this is a good point to highlight. The Thirring model has the same global symmetries as QED3, but the dynamics is distinct. And the dynamics is governed by, obviously, what's the effective action for the A degree of freedom.
So even in the second formulation, when you are talking about U2NF to UN, it's still, there is no gauge symmetry that matters.
No, that the Appelquist argument is purely comes from global symmetries because it's counting degrees of freedom of weakly interacting theories.
Okay.
So it's basically telling you the number of Goldstones which are weakly interacting.
Okay, thanks.
There's no dynamics in it. Okay, so I think it's probably important to get the symmetry right, and I'm going to go on. The method that I've been looking at more recently is, again, drawn from Lattice QCD. It formulates what are called domain fermions using what's called the domain wall formulation. And the domain wall formulation has been specifically devised to get global symmetries, chiral symmetries in QCD, correct. How does it work? You actually introduce an extra unphysical dimension. So for our 2+1 dimensional model, we would label this extra dimension the 3 direction. And I've drawn it kind of curled up in a circle just to get it on the page. So the fermions, as well as propagating in 2+1 dimensions, propagate in a third unphysical dimension with a kinetic term d3 gamma 3. Space-time has open boundary conditions. So there are two what are called domain walls. They have a separation L sub s, which I've drawn as a curved line here. And the way this works is that there are approximate zero modes or near zero modes of the Dirac operator, which are localized on the domain walls. And those localized eigenmodes actually they have the symmetry of the target theory in the lower dimensional theory. So for this particular example, I can identify 2+1 dimensional fields, lowercase psi, as a linear combination of uppercase fields, which are defined in the 2+1+1 dimensions. And they're defined either at position 1 or position ls along the third dimension. These p pluses and p minuses are projectors. They project onto eigenstates of gamma 3. And again, this is a very beautiful idea which was introduced into particle physics by David Kaplan. I said approximate. Everything becomes more and more exact as the distance between the walls is made large. And this is why the idea of the accordion comes in. This is Astor Piazzolla here, and he is trying to take the large LS limit and recover the correct fermion symmetries. There's two ways of thinking about domain wall fermions, and both are useful. So in the domain wall fermion approach, we're doing a simulation in one extra dimension, 2+1+1 dimensions. We're relying on the fact that there are modes localized on the walls carrying the symmetries of the physics we want, and that we're relying on the fact that the modes left in the bulk aren't important, that they can be made to decouple, and that those modes include fermion doublers, which are always present for lattice theories. They don't couple to normalizable modes. And in the world of QCD, by now it's established that it works. It works as long as you choose what's called the domain wall height carefully, and it also works if the background gauge fields are sufficiently smooth. And so when getting the flavor symmetries correct is particularly important, domain wall fermions are a method of choice in lattice QCD, and some really important and interesting work has been done using domain wall fermions. So the question we're now going to explore for the rest of this talk is, can we apply the same technology to a strongly coupled quantum critical point? There's also a top-down view, which is also, I think, more useful from thinking about this from a theoretical perspective. If we think about our fermion bilinear that we start with, in general denoted with a kinetic operator D, then the symmetry that we need can be encapsulated in two anti-commutators and one commutation relation. And then there is a theorem, one of the most famous theorems in lattice field theory, which says that there is simply no regular lattice discretization, which enables you to preserve these relations while simultaneously having unitary local dynamics of a single fermion species. It's the Nielsenninomia theorem. On fairly strong and general grounds to do with renormalization group, it's now believed the closest we can get to obeying these is what are called the Ginzburg-Wilson relations. In other words, we can actually break this. We can have the right-hand sides non-zero for these two. And that looks like, why would that be enough? It will be enough because the right-hand sides, which are non-vanishing, actually should vanish in the long wavelength limit, so as long as this operator D is sufficiently local. It's possible to construct an operator which satisfies the Ginzburg-Wilson relation. It's called the overlap operator. Here it is. A is some complicated function which of a local operator. But the point is this 1 over the square root of A dagger A is a little bit worrying, because what it means is that it's not clear that the overlap operator is actually local. It's not manifest. In fact, it has to be confirmed that it behaves locally. That has to be checked and confirmed numerically. So I'm not going to show you the evidence here today, but just to tell you that we have done it. We have addressed this question in a recent paper. So it looks like there's an overlap operator. It's possible to attempt to formulate that directly and simulate it. That's difficult. The advantage of working with the domain wall fermion approach is that it works with a kernel which is local in 2+1+1 dimensions. So if you're prepared to contemplate working with an extra dimension, you get to write code with much less effort. And if you're an aging professor who doesn't code that well, that's a real advantage.
Simon, question.
Yeah? Sure.
Yeah. How can D overlap involves, I mean, A involves 1 over D?
Yeah.
And how can that possibly be local? That's
okay.
totally
Yeah,
bizarre.
yeah, okay, no. Thanks, Rob. Yeah. Actually, you can do without this non-local bit. You can just have A to be the ordinary local Wilson operator, and that's called the Wilson kernel. It turns out that having this extra non-local bit, it doesn't damage you for appropriate. It's not very non-local as long as you choose this parameter M correctly, and that's called the Shamir kernel. This actually, I wrote it down because this actually corresponds exactly to the domain wall fermion regularization that I'm using. Sometimes it's called the Möbius formulation of domain wall fermions. I'm just blinding you with Technoflash here. I think the short answer is don't worry about it. If you choose M correctly, A is pretty local.
Okay. And the domain wall gives you a local kernel. This is not true in 3+1, correct?
No, it is.
Or am I
Domain wall
mistaken?
fermions are always local. They're local in the extra dimension. As long as if you talk.
Oh yeah, okay,
Yeah,
okay,
yeah.
never mind. Okay.
I'm using local here in the sense of I can code it. Clever people just code the overlap operator from the word go. Okay. I don't want to. I'm going to skip this slide. It's a bit technical. Okay. Let me now start showing you some results. Initially, I'm going to show you some exploratory results taken with a fixed domain wall separation of 16. And I've got 3 different sets of data points here. The blue ones are taken in what's called the quenched approximation. So in other words, there's no fermion feedback. The auxiliary fields A are just drawn at random from a Gaussian distribution. The green points are done with a simulation with 1 fermion flavor. The red points are done with a simulation 2 fermion flavors. The technical slide that I skipped was actually to show that for the blue and the red points are relatively easy to code. They involve something called the hybrid Monte Carlo algorithm. The green points are harder. They require something called the rational hybrid Monte Carlo algorithm, and that took a little bit longer for me to do. The lesson of this is that what I'm plotting here on the vertical axis is the bilinear condensate. And it seems that there's a hierarchy. I get a big bilinear condensate with n equals 0, a smaller one with n equals 1, and plausibly no condensate at all with n equals 2. So this hierarchy is consistent with there being a very sharp dependence on the number of flavors for symmetry breaking. And with the eye of faith, you could say it's also maybe consistent with the critical number being greater than 1 and less than 2. The catch is that this was all taken with a fixed LS of 16. Now, apparently in QCD with dynamical domain wall fermions, LS of 16 is quite a respectable domain wall separation. But we have to go away and check that we're recovering the U2 symmetry. And for that, we need to check the large LS limit. So this is I call it stress testing domain wall fermions. It turns out that it's really quite difficult to achieve the large LS limit. What I'm showing you is the results for bilinear condensate at a variety of different couplings as a function of LS. LS here is ranging from 8 up to 80. And you can see that there's certainly for larger masses and stronger couplings, there's a very strong dependence. Empirically, it seems that we can model the approach to the infinite LS limit by this exponential ansatz here, characterized by some decay delta. These data I'm showing you here are taken at relatively large current fermion mass. However, if I go to a smaller mass, then that extrapolation to large LS is much harder to control. So this is a problem which is getting more difficult as we go towards lighter fermions. Here is that decay constant. I've plotted it. This is quite a hard plot to read, so I'm going to helpfully color it in. It turns out that if you do the fit to this ansatz here at weak coupling, then the decay constant delta is roughly mass independent. These are the points which are falling in this blue band. However, if you do the same exercise at strong coupling, then you can see that the decay constant is approximately linear in the quark mass. And that means, again, that life is going to get difficult. It's going to get hard to extrapolate to the infinite LS limit as I go to smaller and smaller quark masses. These next two plots show the same thing. There's a residual lowercase delta, which tells me how close I am to restoring U2 symmetry. It's basically the imaginary part of the condensate that I showed you. So here's how that residual behaves as I increase LS. It's decaying exponentially. This is a log scale here on the vertical axis. That's good news. The bad news is that the decay rate again is getting smaller and smaller as I go to strong couplings and small masses. Here's another view of the same data. This time it's at fixed LS of 48, and now it's a coupling is going from strong to weak. So at weak coupling, you could argue that everything's under control. At strong coupling, the residual is getting larger and larger and also becoming markedly dependent on the bare fermion mass. So it's going to be difficult and expensive and troublesome to get to the U2 symmetric limit. Independent of that, the actual code itself is difficult to run. I'm typically requiring 20,000 iterations of my matrix inverter routine to get to a solution. That's tough, particularly in a three-dimensional problem. So without belaboring this point, I just want to say that I'm actually using a national supercomputer resource to perform this project. This is not running on a laptop. It's not running on my university's cluster. It's actually running on the Dirac facility. But here's where we've got to. This is still preliminary, but it's taking into account data now taken on values of LS as high as 80 and on both sides of the putative critical point. What I'm plotting here is the condensate as a function of inverse coupling for different mass values. The different colors here correspond to different mass values. Now there's a kind of way of empirically fitting these using an equation of state ansatz. And here's the equation of state I've used. So it's basically the left-hand side is the bare mass, the right-hand side is the order parameter, the condensate that I'm looking at. And these exponents here, these constants, are what are called critical exponents. The critical exponents characterize the universality class of the quantum critical point. So the game that we've been playing up to now is to generate this order parameter data and to perform a fit of this form to the data and see how well we can do. And the answer is we seem to be doing okay. This is a pretty good fit. I should say the reason the error bars look a little bit out of control, this is not raw data. This is data which has been extrapolated to the infinite LS limit. So this data results from a prolonged simulation campaign with several different values of LS. So what I'm going to claim is that we do see an acceptable fit to a renormalization group inspired equation of state, which suggests that yes, there is a quantum critical point at a value of the inverse coupling about 0.28. And that can be, the fitted values of these exponents can be used to characterize that critical point. So here's the answers that we've got. The fitted value of delta is 4.2. The fitted value of beta is just over 0.3. Now, actually, the normal way to do identify universality classes and extract critical exponents in statistical mechanics is to do an exercise called finite volume scaling. And that usually yields two different exponents, nu and eta. So in order to kind of relate that, I'm going to use a hypothesis called hyperscaling. So if I know the space-time dimensionality and I know two of the exponents, I can derive all the other exponents. So this corresponds to values of nu of 0.55 and eta of 0.16. And this, as things stand, is one of the two big results we have for this model. The first big result is that there's a critical number of flavors. It's greater than 1, very likely, almost certainly less than 2. And the critical point that we find at n equals 1 has these critical exponents. It's interesting to compare this result with the results we got many years ago using staggered fermions, which I've already shown you, because the critical exponents there, first of all, the critical number of flavors we found was different. It was between 3 and 4, but also the critical exponents we found are clearly different. So it looks, when I showed that transparency first time around, I said we needed, that staggered fermions were wrong, and we needed better fermions. And I've slightly modified that point of view in the last few months. I don't think staggered fermions are wrong. I think they're different. I think they define a different universality class characterized by a different pattern of symmetry breaking. UN cross UN goes to UN rather than U2N breaks to UN cross UN. And what I've learned over the last half year is that it is in fact possible to write down a continuum description of relativistic fermions with that pattern of symmetry breaking. It was originally done by Kähler in the 60s, and they're now called Kähler-Dirac fermions. So I'm actually my current viewpoint is that there's not just one quantum critical point for the Thirring model, there are two. One of them describes Dirac fermions, and one of them is describing Kähler-Dirac fermions, and they have distinct quantum critical points. In the world of QCD, in the world of weak interactions, you don't worry about the distinction, but in the world of strong interactions, you need to. And that nicely takes me on to my conclusion slide. Before I do that, I'd like to highlight the fact that these results have been obtained in collaboration with Michele Massiti, who's a research software engineer and postdoc working at the Swansea Academy for Advanced Computing, and by my PhD student, Jude Worthy, who's also at Swansea University. We've been supported by various things. I've mentioned Dirac. Igor mentioned the Leverhulme Trust at the beginning. Where have we got to? I think by now, I'm pretty confident we've found a new quantum critical point describing Dirac fermions in 2+1 dimensions. And that critical point has many important properties, but in particular, it's got a critical number of flavors, which is greater than 1. An important observation is that not everybody agrees. So my colleagues in Jena University, led by Andreas Wipf, they've also been studying the Thirring model, but with yet another U2N invariant fermion approach, lattice fermion approach called the slack fermion. And they see a different value for the critical number of flavors. They see it about 0.8. A few years ago, I would have said I'm right and they're wrong. I'm not going to say that. I think we're just in different basins of attraction of a strongly interacting landscape, and that somehow the formulation with domain wall fermions, which I think has more of the character of a gauge theory, is somehow more drawn towards this interesting new non-trivial critical point. However, I believe there's also more than one critical point. I now think that the old staggered fermion studies that I showed you are actually describing Kähler-Dirac fermions with a distinct critical point. Where we're going next is that we're going to be looking at propagated data. We're going to be looking at both propagators of bound states of fermions and antifermions. We're going to be checking which are the Goldstone degrees of freedom and which are the non-Goldstones. I think a more interesting project is also to look at the fermion propagator. I suspect this will be more interesting because it's something that you can't do in QCD because quarks aren't gauge invariant, but there is no gauge symmetry here. I suspect it will also be technically challenging. Independently of that, I've shown you that actually taking the U2 invariant limit is very numerically challenging. It requires this LS goes to infinity limit. And it would be interesting to see if there are smarter ways to access that limit, perhaps using slightly more sophisticated formulations of the overlap operator. That's something that Jude is looking into. So with that, I'll finish. Be very happy to take any further questions or discussion.
Thank you very much. Thanks for a nice talk. Now let's go to questions. Rob Pisarski is question number 1.
Hi, could you go back one slide, please?
Sure. Oh, that's the slide I didn't want to show because it's all the things which don't work. This is the slide you made. Is that the one, Rob?
No, where you had the summary of your result. Yeah. But where you just, yeah.
Yeah, that's it. That's it.
Can you write down what the groups are? I just don't remember. There's too many.
Okay, yeah. For Dirac fermions, it's write down. Can I say it carefully? For Dirac fermions, it's U2n, and that breaks to UN cross UN.
For Dirac.
Yeah. And for Kähler-Dirac, it's UN cross UN breaks to UN.
Okay, so my comment is that, so you don't have results on n equals 2 for Kähler-Dirac? Or is that the same?
I probably do, but what I'm claiming for Kähler-Dirac is that it corresponds to the old staggered results. So
no, there's a technical reason I ask, because the analysis in the epsilon expansion to leading order shows that for the chiral transition, SUN cross U axial 1 breaks to SUN, and that there's no infrared stable fixed point to leading order in epsilon. But there's results by a Japanese group using the conformal bootstrap, and they claim there is a non-trivial fixed point in 3 dimensions.
Okay.
And that's of direct relevance to QCD if the anomaly gets small. So it'd be interesting to see how that overlaps. The other question I had, though, is I just don't understand. Wait, I thought even if you took staggered or something, if you take the lattice spacing to be a millionth, any relevant, if it gets really small, don't you have to approach? I'm missing something. Universal.
I sort of tried to cover that earlier. Staggered fermions will recover the desired U2n symmetry as long as the long wavelength limit is weakly coupled. As long as you recover, in other words, in the limit where the lattice spacing is really small, it's also weakly interacting. And of course, QED3 has that property because it's asymptotically free. And my point was that with my Thirring model, with this crazy 4 fermion interaction, I've got no right to expect that. And I even knew this.
I see. Yeah. Okay.
I even knew this in the 90s. I was told this by Meinolf Gerkele way back in the mid-90s. And he said, just expand this thing with staggered fermions. You'll see there are terms there you don't want, which are not suppressed by powers of A. And I sort of smiled and carried on regardless. And now, 20 years later, those terms which I didn't want are actually there in the Kähler-Dirac formulation.
Okay, so it really is, okay.
They really are different theories.
I get it. Yeah, okay.
Okay, other questions? I have sort of very naive question. If you are going to consider graphene as the practical example of relatively strongly coupled theory in 2+1, which critical theory is most suitable for its description, do you think?
I guess the Dirac one, that's assuming, that's assuming the most naive. The graphene is really perfect, whereas we know that the corrections and due to the bands not being perfectly linear and so on at some stage are important. What I would say with graphene, I wrote a couple of papers on graphene using staggered fermions, and I thought that was fine. But that work's been completely blown out of the water by people doing simulations on honeycomb lattices with realistic interactions, and that's what you should believe. Graphene was a good way into this topic, but I don't believe that I'm doing graphene physics. I believe I'm doing is finding out about strongly interacting field theory, and in particular, stress testing our ability to do non-perturbative calculations with fermions, because that's challenging.
So then sort of the extension of that, when you go to the actual simulation of chiral fermions, let's say in 3+1 dimensions, does this carry over to 3+1 as well?
Well, if you're gunning for QCD, then everything should be fine because you're dealing with a weakly interacting continuum limit. So ultimately you can trust perturbative expansions and expansions in powers of the lattice spacing and so on. Now, there is an interesting hot issue, and it's come from the community of people looking at conformal fixed points in beyond standard model physics. And there are groups who are using domain wall fermions, and there are groups who are using either staggered fermions or Wilson fermions. I can't remember. And it's staggered versus domain wall fermion, and they're seeing different predictions for conformal fixed points, because there again you can't assume the taste symmetry restoration. So you can't. There's a claim, and I think it's still controversial, so I don't want to pronounce on it. But there's a claim that you can't trust staggered fermions for those fixed points either. In other words, you shouldn't trust staggered fermions to look like Dirac fermions, except at an asymptotically free fixed point.
I see. Yeah, well, that's something important to keep in mind, I guess.
Yeah, and I love staggered. I really love staggered fermions. They're great, but
well, but useless, as you say in some cases. Anyway, any other questions before we wrap this up? I don't see any questions from the audience, so let me use this moment.
Okay, wait. I have one last question, if I
go ahead.
Can.
Go ahead.
So I mean, when you were in high school, I did a calculation. It's probably wrong. That suggested that the mass gap is exponentially small in n. So it'd be
Yeah.
e to the minus n. So that's impossible to tell numerically, right? I mean,
I agree. And other people have asked me as well. Yeah, I'm pretty certain that the critical number is greater than 1, but I'm a lot less certain that the critical number is less than 2.
No, I'm asking if it's exponentially small at large n. Can you rule out? Because it'd be a first order, but very, very weakly.
Yeah, atrociously difficult to rule out. It's a problem I want to return to for the Thirring model. You know, when I think I haven't yet put that to bed, but you know, I don't want to say, yeah, I can't say anything any more than that. It's a possibility, and it will be difficult to rule that picture out numerically.
Yeah, it's probably look, I'm probably wrong, you know, whatever. That's fine.
Well, everything's
as
possible.
long as you're not boring. It was an excellent talk, really excellent talk. And I pulled over to listen.
I'm glad you weren't driving when you were asking all those questions.
Okay. Well, anyway, before we wrap this up, I really want to use this chance to once again thank Simon for a very nice talk. It was really a very good talk.